Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss slope fields and separable differential equations. The term differential equations refers to equations where you have both variables and derivatives occurring in the equations. You can have, for instance, x and y, as well as derivatives of y to various orders, even though we don't know how y depends on x and the equation doesn't tell us ostensibly. We have to solve it for y. Well, certain forms of these equations are simpler than the others, especially if we have derivatives only occurring to the first order. We call the equation a first-order differential equation. Actually, the term ordinary is used if there's only one independent variable involved, and so you'll hear the term ordinary differential equation and first-order ordinary differential equation. Often you'll hear mathematicians and physicists call it an ODE, ODE being the abbreviation for ordinary differential equation. To give us something to put a handle on, the general first-order differential equation, actually ordinary differential equation, or ODE, is an equation of the form dy dx equal f of x comma y. That is, here we have some function f of two variables x and y, and we're searching for a function y of x whose derivative at each x is f of x comma y at that x. To be more specific, y equal g of x is a solution of dy dx equal f of xy, provided g prime of x is equal to f of x comma g of x for x in some open interval. That means that when you replace the y by the g of x, and everywhere you see y prime, you replace it by the derivative of g, you actually get a true equation for all x in some open interval. Let's look at a problem where we show that a given function is an actual solution of a given differential equation. Show y equal 1 over x multiplied by the definite integral from 1 to x of the function e to the t over t dt is a solution of the equation x squared y prime plus xy equal e to the x. Notice this is a first-order differential equation because we have y and its derivative appearing as well as x. Now, what we're going to have to be doing, because y involves a definite integral, is differentiating that integral. So for that, what I want to do is recall the fundamental theorem of calculus, which says when I have a definite integral from a to an upper limit x, which is a variable in the upper limit there, f of t dt, well, to differentiate that integral with respect to the upper limit, I just get the integrand f evaluated at x, the upper limit that I differentiate with respect to. So keep that in mind when we start working on this. So what we have to do is begin by computing y prime. So y prime is, well, let's differentiate the first factor, derivative of 1 over x, that's negative 1 over x squared, multiplied by the second factor, definite integral from 1 to x of e to the t over t dt, plus the first factor, 1 over x, multiplied by the derivative of the second factor. Well, remember how the fundamental theorem tells us to differentiate this definite integral. We just take the integrand and replace the variable t with x. So consequently, we'll get e to the x divided by x for the derivative of the integral, and so there's our second term, 1 over x, e to the x over x. You can notice here that in fact we're getting x squared in the denominator, and so we have a common denominator of x squared. I could rewrite this. I'll put the e to the x first, minus the definite integral from 1 to x of e to the t divided by t dt, and this is all to be divided by x squared. So notice what happens when I multiply this equation through by x squared. I get the equation x squared y prime is equal to e to the x minus the definite integral from 1 to x of e to the t divided by t dt. Well, notice, let's look back at our original definition of y. It's 1 over x times the definite integral, so in particular the definite integral itself is just xy. So this is e to the x minus xy. So x squared y prime equals e to the x minus xy. And so if I simply look at the fact that x squared y prime equal e to the x minus xy and move this term to the other side, I get x squared y prime plus xy equals e to the x. And you see that's our original equation. So we've demonstrated that this function y equal 1 over x times the definite integral from 1 to x of e to the t over t dt is a solution of this differential equation. Suppose I have to solve the differential equation y prime equals f of x, where y is some unknown function of x. Well, obviously y is just the antiderivative of f of x, but you know when you antidifferentiate, there's a constant of integration. In other words, whenever we solve a differential equation of first order, there's going to be some unknown constant of integration that enters. That means the solution is really a whole family of solutions parameterized by that constant. So as the constant varies, the solutions vary. In order to tie down the solution, you have to specify the value of the solution at some point. Typically, we use x equals 0, but in any case, if we have a differential equation and the specification that the solution must have a specified value at a given value of the independent variable, that's called an initial value problem. Let's look at a verification that a function is a solution of an initial value problem. Okay, so our problem is to show y equal cosine x over x solves the initial value problem xy prime plus y equals negative sine x with y at pi over 2 equals 0. Notice this is an initial value problem because in addition to the differential equation for y, we have an initial condition. That is, we have a specified value for y at a specific value of the independent variable, namely x equal pi over 2. Well, let's check the initial value first for our proposed solution. If I put x equal pi over 2 in this function, what am I going to get? Well, cosine pi over 2 is 0. And 0 divided by pi over 2 is still 0, so obviously we have our initial value satisfied. So the question is, does this function satisfy the differential equation? So we need to begin by computing y prime. We'll use the quotient rule, differentiate the numerator first. We get negative sine x multiplied by the denominator x minus the derivative of the denominator, which is 1, times the numerator cosine x, and all that is divided by x squared. So consequently, let's look at this, break it up into two terms. The first term is negative sine x times x over x squared. There we could cancel an x and we'll just get negative sine x over x. But the second term is negative cosine x over x squared. And so we have minus cosine x divided by x squared. Well, let's multiply through in this equation by x, and you'll see then xy prime is equal to negative sine x minus cosine x over x. But cosine x over x is y, and so this is negative sine x minus y. So we have xy prime equals negative sine x minus y. And so if I move this y over to the other side of the equation, we get xy prime plus y equals negative sine x. That is, we get xy prime plus y equals negative sine x, which is our differential equation. So this function y equal cosine x over x does solve this differential equation and solves this initial value. So consequently, it is a solution of the initial value problem. Well, the most elementary technique for solving first-order differential equations is the method of separation of variables. It's surprising, however, how often that technique will solve the problem. For separation of variables, we have an equation of the form dy over dx equals some function of x and y, which can be represented as the form f of x divided by g of y. That is, here in the numerator I have a function of x alone, and down in the denominator I have a function of y alone. Now notice that doesn't necessarily mean that I couldn't have f of x times a function of y. If I had a function of x alone multiplied by a function of y alone, I would just take the function of y and put it as 1 over something down in the denominator, and that would give me this form. But the point is, when it's in this form, what I do is, thinking of this as a fraction now, let's cross multiply in the equation, and it gives the equation g of y dy equals f of x dx. And so what we do is simply integrate both sides. So the integral g of y dy is equal to the integral of f of x dx. And of course, we have constants of integration, but it's only necessary to use one. And so on the f of x side, we'll include the constant of integration. And so you see this antiderivative will be some expression in y, and here we have some expression in x plus a constant of integration, and that's the solution to this ordinary first-order differential equation. Let's solve a differential equation using the technique of separation of variables. Here I want to solve the equation 2 times the square root of xy times dy dx equals 1, and I'll add the provision that x and y are positive just to make sure that square root makes sense. Notice that I can separate the variables because this is dy over dx equals 1 divided by 2 times the square root of xy, which is 1 divided by 2 square root x square root y. And so consequently, I can just get all the y variables to the left and the x variables to the right. So let's multiply by square root y, and I get square root y dy over dx equals 1 over 2 square root x. And now multiply both sides by dx, and we have square root y dy equals 1 over 2 square root x dx. And so what we do now is simply integrate both sides and add our constant of integration. So putting in another sheet here, we have integral square root y dy equals integral 1 over 2 square root x dx plus a constant. So let's carry out the integrations. Square root y is y to the 1/2, so the antiderivative is y to the 3/2 divided by 3/2. Let's take out the constant 1/2 from this integral, and so we have x to the negative 1/2. Its antiderivative is x to the positive 1/2 divided by 1/2 plus the constant of integration. Notice the 2's cancel here, and so we have y to the 3/2 is equal to x to the 1/2 times the constant of integration. Of course, we have to multiply out the 3/2. And so we have y to the 3/2 equals 3/2 times, I'm going to write the x to the 1/2 as square root x plus 3/2 times our constant of integration. And what I'm going to do is simply absorb that 3/2, which is purely a number, into that constant. And so I'm not going to change the symbol for it. Alternately, you can think I can use one symbol for the constant here, maybe c with a subscript 1, and then after multiplying c1 by 3/2, I get another constant, which I'll just call c. Well, in any case, now you can see that because x and y are greater than 0, I can use exponential rules to solve the equation. I just take the 2/3 power of both sides and I get y isolated. Y is equal to 3/2 square root x plus the constant of integration c, all raised to the 2/3 power with x greater than 0, and of course y greater than 0. Well, let's use the technique of separation of variables to solve a first-order differential equation involving the exponential function. Solve dy dx equal e to the x minus y. Well, unless you're familiar with the laws of exponents, you're not going to realize that this right-hand side is actually a product of two functions. Remember, e to the x minus y is the same as e to the x times e to the negative y, which is in effect e to the x divided by e to the y. So I'm multiplying both sides by e to the y and multiplying both sides by dx. We get simply e to the y dy equals e to the x dx. So now we just integrate both sides. We get e to the y equals e to the x plus a constant. In other words, obviously the antiderivative of e to the y with respect to y is e to the y, and same for e to the x. So these integrations lead to this simple form, or we can say e to the y minus e to the x is a constant of integration. If you wanted to isolate y here, notice e to the y being equal to e to the x plus c. To solve for y, you just take the natural logarithm of both sides of the equation, and the natural log of e to the y is y, and so we get y equals natural log of e to the x plus the constant of integration. Let's use separation of variables again to solve a differential equation. So here in this problem, we want to solve the differential equation square root x dy over dx equals e to the y plus square root x. Okay, so why don't you pause the video, try this one on your own. Remember, it's separation of variables, and then we'll see how I do it. Okay, so the key here in separation of variables is to write these functions, so on the right side here, as a product of a function of x times a function of y, and that's what the law of exponents allows us to do. This is e to the y times e to the square root x. So now let's get all the y's over to the left and the x's over to the right. That means dividing by square root x, multiplying by dx, and multiplying through by e to the negative y. And so we get e to the negative y dy equals 1 over square root x e to the square root x dx. Well, now what we want to do is integrate both sides. So I'll put in the integral symbol, and of course we'll get a constant of integration on the right. But the left-hand integration, e to the negative y dy, is certainly very easy. That's obviously just the negative of e to the negative y as an antiderivative of e to the negative y. And so that equals the antiderivative of e to the root x over root x dx plus a constant. Now to perform this integration, the way to go is substitution. So what we want to do is substitute u equals square root x, then du is 1 over 2 root x dx. That is, the dx over root x is 2 du. Let's multiply out the 2's. We can see 2 du is 1 over root x dx. And so when we replace 1 over root x dx by 2 du and the root x up here by a u, we get twice the integral e to the u du and plus our constant of integration. Of course, we have to remember that our u is square root x. So now we get negative e to the negative y equals 2 e to the u plus a constant, which is 2e to the square root x plus a constant. So, for instance, if I put the 2e to the root x and the e to the negative y on the same side by moving this over and switch the constant over to the other side, this could be also equivalent to the equation 2e to the root x plus e to the negative y equals constant. Okay, now let's solve a first-order differential equation where we have to deal with radicals. Okay, let's solve the differential equation dy over dx equals 2x times the square root of 1 minus y squared. In this one, we can easily see how to separate the variables. Just divide both sides by the radical and multiply out the dx. And we'll get dy over square root 1 minus y squared equals 2x dx. So now we integrate both sides. Antiderivative of 2x is simply x squared plus a constant of integration. It's the left side here that's going to cause us some trouble. And here we want to make use of the Pythagorean identity, which says 1 minus sine square is cosine square. And so we're going to set y equal to sine theta. Then dy is cosine theta d theta. And what about the radical? Well, 1 minus sine square is cosine square, and square root cosine square is just cosine here. In this range, we will have cosine theta positive. And so consequently, our antiderivative becomes simply antiderivative cosine theta d theta divided by cosine theta. And so consequently, what we get on the left side, the integrand cancels out. We just have 1, and so the antiderivative is simply theta. Now, theta is inside this thing we substituted. We substitute y equals sine theta. So how do we get from theta back to y? Well, if y equals sine theta, then theta is arcsine of y. And so that means our arcsine of y is equal to x squared plus the constant of integration. Or if I wanted to take the sine of both sides of the equation, that would give me back y. Y is equal to the sine of the quantity x squared plus an arbitrary constant of integration. Okay, we've solved some differential equations using the method of separation of variables. Don't forget, whenever you solve a differential equation, it involves integration somewhere, so there has to be a constant of integration. In the case of an initial value problem, what you do is, after you've solved the differential equation with that constant of integration, you take the independent variable's given value and substitute that in for x or whatever the independent variable is, and set that equal to the specified value at the initial value problem. And then that gives you an equation for the constant of integration for its specific value to make that initial value happen. So in any case, when you're solving these differential equations, the first technique you should always look for is the technique of separation of variables.